Hello and welcome to Junior Engineering. On this channel, we discuss mechanical engineering in general and simulation in particular. We also discuss the ramifications of mechanical engineering, especially technical mechanics. Today's topic will be the first video about enhancement of the code Aster test or tutorials. Enhancement don't mean better results or simply reproduce the same analysis, but it means addressing them in a more practical way such that they become more attractive for a newcomer, for example. So like a complete analysis, we will do modeling and first steps of preprocessing with FreeCAD, and then complete the preprocessing and meshing in Salome platform, the computation in Code Aster Solver, and finally the post-processing visualizations back again in Salome platform. So let's go. A cylinder in vertical position. The problem is a cylinder in vertical position is charged with a hydrostatic pressure. Determine displacement at 4 bottom and top inside and outside points. So we have a linear course of pressure from 0.2 megapascal to 0.0 megapascal. The cylinder has a height of 4,000 millimeter and an inner diameter of 2,000 millimeter and outer 2,200 millimeter. Also, the local reference with red x-axis is located at the bottom. The dimension will be in millimeter, otherwise in SI units, in order to obtain the displacement in millimeter and eventually stresses in megapascal. So to the boundary, as boundary condition, we have LD inside, which is the load on the inside. We have SP ground, which is located, which is the circle plane. We have CPA, CPB, CPC, and CPD, which are points on the surface boundary. CPA and CPD are on the same line inside, on CPB and CPC on the outside. So we have the reference origin is located on the circle plane in y equals 0. Keep in mind that the definition of a name geometry, at least if you want to follow modeling. So the SP ground is the support on the y equals 0 circle plane, dx equal dy and dz equals 0, and LD inside where we apply the pressure P in megapascal, and the pressure is a linear function. P equals 0.2 minus 5e minus 5 y in the y direction, and we have some control points for displacement output, CPA, CPD, CPB, and CPC and CPD. Like I said, CPA and CPD are on the same line, and CPB and CPC also on the same line outside. So what we want to achieve is to match these displacements from code Aster 17 Aster format 00A. CPA with dx equal 0.010 millimeter and CPC minus 0.0053 millimeter, and we want to reproduce these values, at least to have them. So format 00A uses an axisymmetric modeling, and we a 3D one. Of course, with a axisymmetric modeling, the axisymmetric modeling is way simpler and quicker to set and compute. But a 3D modeling practically more understandable for the newcomer. That's also the goal we want to achieve. So now to the modeling, we open FreeCAD and create a new document and save it right away. We can rename the document as tooth000A. So we create a new sketch. Okay. And we sketch the base of the cylinder with 2 circles. So the diameter in this case the radius is 1011 millimeter, and the second one 1000 millimeter. All right. So 2000 millimeter, 2200 millimeter. The radius are the halved. So we create a pad with a length 4000 millimeter, the height of a cylinder. Okay. So obviously we've done the pad in the z-axis direction, and we don't want that. We want it in the y-axis direction. So the green axis direction. So change the sketch attachment to the XZ plane. Attachment editor, and choose the XZ plane, and okay. So actualize or recompute. All right. So it isn't clear if the pad direction is positive, so we can check that. By querying a point. So it's in negative direction, we have to reverse the pad direction. Okay. So we want to make the tutorial more interesting by using 2 kinds of meshes with tetrahedrons and hexahedrons. So the strategy to have hexahedrons is to extrude the part. For that, Salome S mesh needs a 8-corner block, otherwise the algorithm will not be available to choose. So we can have 2 8-corner blocks by axially splitting the cylinder. The splitting tools will be a plane through the diameter, and in order to create that, we need one more surface line boundary. We can have this line by adding a pad. So we create a one more surface boundary, choose the top base and create a new sketch. So we need only half of the base. So you can export the base as a construction geometry. So we need horizontal line in order to close the sketch. So we need the sketch under constraint. We have 2 degrees of freedom which are free. The first one is here. We can constrain the point on the horizontal axis and the other line also. All right. So we create a new pad through the length of the cylinder or the height of the cylinder, reverse direction. This will create an additional surface boundary. All right. We can make sure that we have a full length by changing the type. All right, we have so bear in mind we still have only one cylinder body, but with additional surface line boundary, which will now help us in the next step. So we need now the rule surface in order to split the body. So change in the part module. In the part module, select the 2 outer lines with control on the keyboard. This is the bug in FreeCAD, but they are selected. So now rule surface, et voila. We have a plane, and we'll use this plane as tool in order to split the cylinder in 2 halves. So select the 2 in the construction tree and then slice apart. And here the result. We have 2 8 corner blocks we wanted for an extruded hexahedral mesh. So you can check if everything is all right. 8 corner block, or in this case half of a cylinder, which can be easily extruded. It's very important to have that, otherwise will not the algorithm will not be available. So now we can export the result as step file. You can keep the same name, millimeter. Okay. And we've done with modeling. Yes, the result. So now we will continue the pre-processing by defining the boundary condition names and so on. So open Salome platform, switch in the geometry module. You can save right away under the same name, tut00e. All right. So now we can import the step file, the geometry as step file. So take into account the units millimeter embedded to the file, ignoring which will cause model scaling. So we don't want that. Then choose no in order to keep everything in millimeters. Then no. All right. So this is the model. We always need the reference in order to find the right base, the top and the bottom. All right. You can rename tut00a. So don't forget that we have a compound slice 0, slice 1, which we can explode in order to have the two entities. Then new entity explode, subshape type solid, apply and close. So we have the two solids, slice 1 and slice 0, which we can rename as volume 1 and volume 2, V1 and V2. Okay, so next step is now the boundary conditions. or the control point. We have SP ground, LD inside, and the control point CPA, CPB, CPC, and CPD. So we will define them. New entity, group, create group. So first we will want to create the faces, or the surfaces of the faces. In this case, SP ground and SP LD inside. So first SP ground, it is a surface. Don't select surface, choose the base at 0, 0 and apply. So we have an entry in V3. So next is LD inside. The inside surfaces, the two inside surfaces where we will apply the pressure. Always select with you can select every surface, then apply. We continue. Now we need the control point, which are point, then change to the shape type point. Then the first one CPA, this point, and to magnify in order to see clearly. The CPA. Shape type point selected, that's CPA. Select the point, add and apply. And the next one CPB, and with CPC, apply, and CPD. You see, CPD and CPA are on the same line inside the cylinder. We have finished apply. Here are the 4 points, 4 control points. So now we need to define the line of the surface we want to extrude, the top surface, the top base of a cylinder. The 4 lines on the top base. We will use this line to subdivide the surface and then extrude it. So we can name it CS then we can restrict the selection in order to choose properly. And then V1 apply. So next are LS, we name it LS. The small segments, the first one are those of V1, then select, add, and restrict to V2 yet, and the small segments, add 4 in total. We forgot the first one. All right. So you will use them to subdivide the surface, the base, and then extrude it. So we can check if everything is all right. So the circle and the small lines are there. Okay, we are so far finished with the pre-processing. You can now switch in the mesh module. So select the and mesh, create mesh. So we can keep the same name throughout the analysis. So we'll automatically create all group on geometry. So this mesh should not contain any algorithm because we'll extrude the two V1, V2. So keep the algorithm no one, 3D no one, 2D no one, 1D no one. So we'll use it only as a container for submeshes. So select the mesh and create submesh, mesh, create submesh. So the first one will be select the V1 in geometry. We can keep the same name. And now extrude 3D. You see, we can choose this algorithm because we have a solid, a 8-corner solid, which we can extrude. Then 1D wire discretization. Will choose number of segments, so we can keep the same name. Here will be the number of elements in the extrusion direction. Then the name, so we can take for example 100 elements. All right, the extrusion is done in the length of the cylinder, in the height direction. Okay, apply. So the next one, V2, both bodies are the same, so we change nothing, then apply. So now to the subdivision of we don't have the face, the base we want to extrude, so we will come back in the geometry in order to define it. But first we can continue. It is same as SP ground, but on the top. So that's why we cannot use SP ground. So we continue with the submeshes. So the next one will be the subdivision of the base surface. So it's a line, wire discretization. So these are the circle. You can choose 50 elements or 50 nodes. Okay. These are the order of the meshing process, but we'll come back to it because we are not finished. So the next one, LD, LS, with small segments on the base. So we can take, for example, 5 elements or 5 nodes. So now, yes, you see, we want the algorithm to first mesh the lines and then the solid. So you can choose you can change the order. Blind goes. So we need yet the surface, the top surface or the top base. We have to define an additional geometry, which is with top surface we want to extrude. So create a new group. You can name it FS, faces. So the top two add first and apply and close. Okay, we'll extrude this surface. Okay, come back in the mesh module and create another submesh. Choose FS, which is a surface. 2D, we want quadrangle mapping. 1D, we don't need 1D. Apply. Okay, all right. We have everything so far. We can launch the meshing. Maybe we check the order of the meshing first. So everything all right. Okay. Plan close. So we have everything so far. So select the mesh and compute. Or you can go in the menu, mesh, compute. So you see, this is the result. We have only volumes, hexahedrons, 50,000 hexahedrons. Only quadrangles, no triangles, and volumes we only have hexahedron 50,000. All right, that's what we wanted. So we can first check the mesh for some error or irregularities. So you see we have a bad ratio here on the face. Can check it. Face controls, face control, aspect ratio, you see, it's very red. Can't read. 188. It's very bad, but it's not a problem for such a analysis. But we can better by increasing the subdivision. So on edit submesh, rather than 15 we can take, for example, I don't know, 80. Okay, so we can compute now. It's better now. So it's red because it's where we have extreme values, but the values are now better. The aspect ratio is better. Oh, reset. We are finished with the first mesh. Now we are not finished because we have a compound and we have to glue both together. Can check it because we don't want to have two meshes. So no free node, connected element 8, but the number of double nodes are very important. We don't want to have double nodes. So we will of course have double node, 2400 double nodes. We don't want this. We'll correct this in a minute. Double phases, no. Over constraint, aspect ratio diagrams very good. It's 1, near 1. Most of them, at least. And here, of course, the base elements have bad aspect ratio about the volume. So we don't want double nodes. We will glue the nodes at the connection of both volumes. So modification, transformation, merge nodes. So we want to keep the control point, otherwise they will be glued and gone. So node to keep during the merge, then select the 4 control points. Apply and close. You see, 1212 groups of nodes successfully merge. So all right, so we can verify if we have double nodes. See, no double nodes, very important. We can also check if we kept the control point. See, we have CPC which is kept, CPD which is also kept, and all right. Save time to time. So now we have to merge elements. And always take out the control point, otherwise they will be gone. apply and close. See, 1420 elements successfully merged. So this is very important in order to keep only one mesh. We don't want to have two groups of meshes. We have only one mesh in the definition. So we have we kept the four control points: CPA, CPB, and CPC, and CPD. So you can check the mesh for quality. No double nodes, very important. No double edges, no double faces. All right. So okay. So we finished so far with the hexahedral mesh. You can check no double edges. Skewness, very good. Everything blue. Aspect ratio, as expected. On the basis, we have the extreme values, not necessarily bad, but the extreme values, which are red. The aspect ratio, of course, on the outer diameter element. No double volume. All right. I set everything. We are so far finished with the hexahedral mesh. Now we need the second mesh, which is made of tetrahedrons. Can rename first X and save. So create a second mesh, create mesh. I'll name it tooth AA. So NetGene in 3D, NetGene 2D, and in 1D length from edges as hypothesis. In wire discretion, here we choose local length, not number of segments. So we now have to think about a good length of element length. So we can choose, for example, I don't know, which value can be so bear in mind that this is in millimeter. So we can think about 10 millimeter, or I don't know. So we can try with 10 millimeter first. So NetGene 3D, NetGene 2D, and 1D element length of 10 millimeter. So we can compute now. First rename it tet and compute. So maybe 10 millimeter it's too small. I don't know. You can check first if the computation take longer. 10 millimeters, it's very small. Okay, we can cancel and increase the element length of the subdivision length. 10 millimeter is too small. So, all right. Okay, we have 20,000 tetrahedrons. 20,000 tetrahedrons. So this is only due to the display mode, like on shading. All right. And check the base. Can edit mesh. 150 length. 50 millimeter. Can try because 100 too big. This take too long, but let's see what we have. So it's better, but we have increased the number of elements. So the border are quite well meshed. So now we do the same with gluing the nodes. You see, 848 double nodes. Volume. All right. So okay, modification, transformation, merge nodes. Take out the control point, CPA, CPB, and CPC, CPD. Add, plan close, and then transformation, merge element. Take out again the control point. All right. Save. No double node, no free node, no double node, no double faces, aspect ratio, the mouse by one, no double volume. All right, okay. Can do some controls of the mesh. Skewness is, some elements are very bad, but this is not the aim of the analysis. We can better the mesh, but for a linear static analysis, it's quite okay. The mesh is quite okay. So we have two meshes, 80,000 hexaedrons and 96,800 tetrahedron. So we export both meshes as MED file, of course. So, and we are done with the meshing. So now to the analysis settings. We use two command files, tooth-A1 and tooth00A1 and tooth00A2. So one for computation and the other for post-processing. After the first ends, the intermediate results will be saved and initialize the second. We don't necessarily need that for this lightweight analysis, but it can become crucial in long-running cases where the command execution can stop after an error and cause the deletion of the data stamp. So having the data from time to time saved is a good practice to adopt. So this is the folder of the analysis so far. So we begin with some comments on the head. The units are in millimeter, kilogram, megapascal, and the reference is of course quad Aster format 00A. So we begin with the definition of some variable, the Young modulus, Poisson's ratio, and the pressure, the Young modulus first, which is megapascal. The Poisson ratio, nu, which is 0.3. Now the pressure at the bottom of the cylinder, which is 0.2 megapascal, and on the top 0.0 megapascal, a linear function. So this is the function. It is a linear function. We need only two points on the bottom and the top. So now the process starts with debut, to begin. Then after that we read the meshes, mesh tet and mesh hex. It's very important to define two channels, 20 and 21 for the reading. So then we defined 3D mechanical models. These are 3D models, one for the tetrahedral mesh and hexahedral mesh. Then we defined the model by assigning a model, a model. So for that we need the mesh, which we defined earlier. Then the assignation. So model concern all the mesh 2V, and the phenomenon is mechanic, phenomenon mechanic, and the modelization is 3D. So we do the same for the hexahedral mesh. The difference is only the meshes. So model hex with the hexahedral mesh. The variable where the mesh is saved and okay. So now we define the material. We name it steel. Define material. So define material. It's an elastic material with Young modulus and Poisson's ratio. These are the variables we defined earlier. Young modulus and the Poisson's ratio. So now we assign the material to the meshes. The material we defined now. So we need for that variable as matter tet. So we assign the material. For that we need the mesh, and we need the assignation, all the mesh and the material name. This material name. So it's the same for both. The difference is only the meshes, the name of the meshes. So now to the boundary condition. First the supported. So for that we need the model we defined earlier. And we want to apply on the face the mesh group SP ground, which is the base of the cylinder at the reference origin. dx equals 0, dy 0, and dz 0. SP ground, dx 0, dy 0, and dz 0. The base of the cylinder. So we do the same for the hexahedral mesh. We need the model for that. And after that we define the pressure, a function, the pressure function, because it is a linear function, 0.2. So we define the function, and the function parameter or variable is the y coordinate, because in the y direction. like you see here in the FreeCAD model. So along the height of the cylinder, this height, so, and now because the linear function, we need only 2 points, one on the base where the pressure is maximal, 0.2 megapascal, and one on the top. By 4,000, the height of the cylinder, where the pressure is 0. So after defining the function, we assign now the load, the pressure load inside the cylinder, aperture meter F. So the F means we want to use a function. So we need for that the model and then a pressure load. The group of mesh, we need LD inside, and the function we defined earlier, this function, so the pressure value is the function. So one for the tetrahedral mesh and one for the hexahedral mesh. So the difference is always the meshes or the models. So after that, we compute now a linear static analysis. We compute both models and we save the result in variable result tet and result hex. So the computation needs the model and then the material field. It's the assigned material. So assigned material to meshes. These are material fields on the meshes. So the material fields and the load. As a support is also load. So we need the support and the load, the pressure load. The support and the pressure load. So we do the same for the hexahedral mesh. Model, material field, and load, support and load. And then end, fin. So after that, we intermediate result will be saved. And yeah. So to the second command file, we continue the analysis with pursuit, not with debut, but with pursuit. So now to enrich the results, the computed result with some post-computed fields, computed fields. For the enrichment, we need, of course, the results, calculation, so calculate fields. So we reuse the results we computed for the mechanical for computation, result tet and result hex. and then we need the fields we want to compute it. We want to compute here von Mises stresses. It is a choice. We can compute a lot of fields, but for example, in this case, we want to compute some von Mises stresses. So now, like you see, the result of the computation, and also in this case, so now we print the displacement at the control point in readable file. CPA, CPB, CPC, and CPD. Where will be printed in a file which we can read. The format is, of course, resulta. The first one CPA, CPB, and CPC, CPD. So format is resulta. So we have a lot of format. If you know that, we can check the syntax of the command by going on the documentation of the code Aster. We search imprimer result. Result idea, Aster met Gimesh, and so on. This is unfortunately in French, but you can use a translator to translate some part of the documentation if you are interested in some information. So we continue. We need, of course, the model, and then we print for both meshes in a single file. One for the result for the tetrahedral mesh, and the other for the hexahedral mesh. So we need the node groups, of course, the name of the control point, the format of the results. This is a Fortran format. So this is for the tetrahedral mesh, and secondly for the hexahedral mesh. We want to print the displacement, the control point, on the control point, the format, and we give some title in order to find easily the results of both the tetrahedral mesh and the hexahedral mesh. So finally we print the result in the met format in order to do some visualizations. We want the displacement and the displacement and the von Mises stresses to be saved. One for the tetrahedral mesh and the hexahedral mesh. We give also names in order to discriminate the name, the databases, and we have end. So the computation begin here, the analysis in 2001, and will be save, which will save the intermediate results, and continue with tut 2002 command file. And yes, we are finished with the definition. Now open code Aster, and we will set the files for the computation. Create a new ASTK file. We named it. So we need first the base path, where the this is where the analysis file are located. So we can simply copy the path. So, and now we need to define the files of the analysis. First, the two command file. So the absolute path, you can simply copy, or the first one /back 200A1, also /back 200A2.com. So we need to define the mesh. We need two meshes in the analysis at channel 20 and 21. med. We don't need compression. So 20 and 21. So we need the name of the meshes in the folder, analysis folder. Not this name. 2008 TETSMED and 2008 HEXMED. The other one is HEX. All right. So the next is we need also to define a file for the displacement at the control point and the result for the visualization. So the first one is resu for result. Resu. And AirMed for the visualization. You can keep. So simply copy one file path and modify it. The first one is resu. You can simply keep 200a.resu, and the second one 200a.airmed for result on the channel 80. So finally, we have to save the base files for the intermediate results. So it's only a folder, the base. So we don't need a file extension here. So we want to save it first. That's why we keep only, we only have to check air as a result, no compression. On a copy path first, and base. We name this, it's a folder, so only folder, no file extension. So now finally the message file in order to monitor the computation. So tooth00a.mess. All right, we are finished. We have to save the analysis. All right, can check it. See, tooth00a astk. It's a file with a setting for the computation. So what can we do now before launching before running the computation? Okay, we can set some options like the number of CPU for the computation if you want to compute it parallel, for example, and other stuff. Okay. All right. So we are ready for running. So run. So you can refresh right away in order to check if we have some syntax errors. Yeah, it's running. All right. So this can take a while. If you want, you can make a pause. I don't know. Do some stuff. So end it with alarm. So it's quite good. So this is the base file. You see, it can be very, very heavy. This is a message file. So you have to check the computation time of first the alarm, where the alarm comes from. We have alarm. Yes. So it's a memory problem. You see, it's meant it can take longer because we don't have enough memory. So you can always the total memory. You can increase the total memory of the computation time if the computation takes longer, in order to have optimized settings. So you see, this is the state of the analysis folder so far with the results. This is the message file. Every command will be processed with statistics. This is the tetrahedral mesh. We have now the computation of tetrahedral mesh, and this is the time. The computation takes 30 seconds, quite quick. And for the hexahedral mesh, we have 10 times the times of the tetrahedral mesh, 300 seconds. It's very quiet. You see the difference. So 10 times the 30 seconds. As a 30 seconds for the tetrahedral mesh and 300 seconds for the hexahedral mesh. So you see, this is the end of the first command file, the saving of the object. all the variable we defined and the result of the computation. This end. At this end, this file or this object are saved. So this is the statistic of computation. We also have the time of the execution time of each command. See, 30 seconds for the tetrahedral mesh and 300 for the hexahedral mesh. This is quite a lot. The difference is big. So, as we have a lot of information in the message file, and here the second command file begins with a reading of the reading of the base files. See, this base file will be read. So after the reading, we have again the variables, and now the execution of the command, and at the end the objects are saved. Here, for instance, in the visualization results, in the AirMed file, for instance, and yeah, this takes only 19 seconds. The second file, the second command file takes only 19 seconds. So to the results. So first prediction, because we constrained the ground with dx equal dy equal dz equals 0, we cannot expect the displacement of 0.01 millimeter at the control point A, CPA. Code Aster raises an error about singular K matrix because of insufficiently constrained degree of freedoms. If we choose the boundary condition used in format 00A of code Aster 17, we will get a singularity error. So that's why we constrain dx equal dy equal dz 0 equals 0, the base of the cylinder. So we cannot expect the first values CPA. We can only expect 0 because we constrain it to 0. First, we have to open the result file, which are of course in millimeter. So first the concept, we can find again the concept. So we see here one for the tetrahedral mesh and one for the hexahedral mesh. It's a computation. Yeah. So we can use that to discriminate the results. So the format is of course 7-digit. That's why we use some subtitle in order to find them easily. So the control points are in this order: CPA, CPB, CPC, CPD. the first line, second, third, and fourth. And like you see, we have 0 at CPA, 0 dx0, dy0, and dz0, and we cannot expect the first result. So we have, of course, this for the hexahedral mesh. So in this case also we have different values, at least in the y direction. So for the second value, minus 0.0053 millimeter, it's a minus, I forgot a minus. We have minus 0.0049, which is quite the same. So in the case of a hexahedral mesh, we have minus 0.0049. In tetrahedral mesh, we have minus 0.0046. And these values are pretty close to each other. So one thing, if you look at the tet and the hex results, generally the values for the point inside the cylinder, CPA, as a value for CPA and CPD are dramatically different in absolute dy value and sign. This needs to be more investigated if the values there matter. So we are done with a displacement result. We can switch to the visualization. So for that, we come back to Salome platform, and we switch to Paravis for post-processing task. This can take a bit longer to switch in the module. All right. Then the pipeline browser, we can open the result file, which is AirMed. AirMed is the visualization result. Okay. Then apply. So all right, so this is the displacement which you can. So first check for realistic results is the smooth continued gradient of a displacement field from blue to red and vice versa. So the displacement value range from 0 to 0.00873 millimeter, which are reasonably in the area of linear elastic. So what we can do now is also to check here in the viewer the values of the control point. The first A, which is the third line, which is of course 0. And here for CPC in the Y direction we have minus 0.00455,048, which is what we needed. So all right, so we can save time to time the state of the analysis. So don't forget we save 2 data sets for the TET and the hex mesh. We can switch the results. The values are the same, like you see, the range at least, and the continuity of the displacement gradient. We can also switch to surface with edges. Like you see, that means for this first computation round, both meshes perform the same results, although obtaining hexahedrons take quite a bit longer. But in general, hexahedrons give better results. So, all right. So we reach the end of the tutorial. Thank you for being here. Let me know your remarks in the comments. If you like this kind of content, click on the notification bell or subscribe to our new videos. Goodbye and see you soon.